Hello and welcome to lecture 11 for the course on aerodynamic design of compressors and fans. In last lecture we have discussed one of the tutorial that's what was based on different configuration, we say stage configurations. Now with these fundamentals let's move ahead. So here today we will be discussing about the aerodynamic aspects of our axial flow compressor. In order to understand, if you look at, we are having an airfoil. This is an airfoil. We can say this airfoil as say uncambered airfoil, or we can say as a symmetrical airfoil. So we know airfoil, it is defined as an aerodynamic body. Okay, that's what will be giving a distribution of my pressure on upper and lower surface. If I am talking about the symmetrical airfoil, for that I will be having equal distribution of pressure. That's what will not be generating any kind of lift. Now in order to generate the lift, there are different means. One of the mean is I will be giving my flow at certain angle here. That's what will be changing the distribution of my velocity on the airfoil, and that's what will be changing the distribution of pressure and will be giving me the lift. But for our purpose, for axial flow compressors and fan, these airfoils, they are being used for different purpose. We have seen in last few lectures, say we are having different flow angles. That's what we say blade angle or blade air angle. That is what is giving me my beta 1 and beta 2 at the entry and exit. That's what we say delta beta. Now if I'll be incorporating those angles, that's what will be giving me this kind of airfoil. Okay, so here if you look at my flow, that will be entering at some angle beta 1 and my flow will be leaving at some angle beta 2. This is what is called cambered airfoil. So for our compressor and fans, we are using cambered airfoil. This is what is having lower angle, that's why, or lower camber angle, that's why it is defined as a low cambered airfoil. Now we know the property of airfoil, that's what will be giving me my lifting force. So we must realize, we have discussed earlier also, I will be having more pressure here or say large pressure here compared to my say upper surface. So let me introduce that upper surface, that's what is known as a suction surface. This lower surface, that's what is defined as a pressure surface. So on pressure surface, I will be having higher pressure. On my suction surface, I will be having lower pressure. This differential pressure, we have realized that's what is because of how my flow that will be moving ahead. Okay, and with say imaginary streamlines, we have discussed how my flow, that's what is moving on my suction surface and my pressure surface. Now perpendicular to that force, that's what is defined as a drag force. Our major interest, that's what is on the lift force. Now let me introduce a new kind of airfoil here. So here if you look at, this is what is having my angle, blade angle, that's what is very large. That's what is called say large cambered airfoil. This large cambered airfoils, those we are using for turbines. Now let's try to understand here, for this also I will be having my lifting force, I'll be having my drag force. So this phenomena what we are discussing in sense of generation of lift, that's what is common for wing. We can say for now cambered airfoil, that's what we are using for axial flow compressor. My cambered airfoil for turbine, they are also generating the lift. Okay. Now in order to understand this part, let me put this as a force. So this is what we have discussed as a lifting force, and I'll be having drag force. Now here in this case for the compressor, we know my pressure at the entry, that's what is lower, my pressure at the exit, that's what is say higher. Okay, that means if you remember, we are used to say in aerodynamics or even in our fluid mechanics, we used to say when my entry pressure is lower and my exit pressure is larger, that's what we are defining as a adverse pressure gradient. So now using differential pressure, I will be using adverse pressure gradient. Okay. Now in line to that, if we are talking about the turbine, where I'll be having my entry pressure, that's what is large, and my exit pressure is lower, and that's what we say as an expansion process, and we need to say this as a favorable pressure gradient, because my flow that will be moving from high pressure side to low pressure side. Okay, so that's the reason why we are having two different airfoils. You may be having questions, sir, what is the reason why we are having this kind of low cambered airfoil for compressor, why we are having high cambered airfoil for turbine? We need to realize here, when we are working under adverse pressure gradient, mainly because of adverse pressure gradient, I will be having more chances of my flow to get separated. My flow will be getting separated mainly from the suction surface. Okay, so majority of work or majority of research, that's what is going on, what is happening on the suction surface of your compressor blade and what is happening on your suction surface of the turbine blade. Okay, now here if you look at, these are the two airfoils I have arranged in such a way that this is what is representing my flow passage. And as we have discussed earlier, here we are having this inlet area and this is what is say my outlet area. If I say my entry area is lower, my outlet area is larger, we can say this passage as a diffusing passage. Okay. Now if this is what is your case, you just look at this is what is a second arrangement. Okay. Here in this case, if you look at carefully, here I am having my entry area, this is what is my exit area, and if you look at carefully, my entry area is larger and my exit area is smaller. Okay, that means it is making say converging passage or nozzle kind of configuration. So now onwards, as and when you will be looking at the blades, you must realize, is it a compressor blade or say turbine blade? What are the two ways? You just look at what is happening between the passage and just look at the camber of that airfoil or camber of that particular blade. Okay, so as we have discussed, we are having our lifting force, that's what is acting in this direction, we can say from pressure side and the suction side. If we realize, this is what is representing my lifting force. My flow that will be entering in the passage from this direction. Now in compressor, we want to compress our working fluid. So we want to do work on our working fluid. In order to do that part, we want to utilize our lifting force. This is what we have discussed earlier also. So basically the purpose of using this airfoil, it is to utilize the benefit of your lifting force. So what it will be doing, we want to use this as our say benefit for our application. Then I need to have say my rotation of wheel that need to be from my suction side to the pressure side. So if you look at carefully, my flow will be entering from this side. When it is passing through that, we are taking the benefit of this lifting force, and that's what will be helpful for us in order to compress my working fluid. Now in line to that, we are having turbine blade, in that also we are having lifting force. Now when my flow, that's what will be passing through this passage, I want to extract the work from my working fluid, because we are using this for our expansion process, or we want to extract the work from our turbine blades. So what we need to do, in order to take the benefit of this lift force, we need to rotate our wheel from pressure side to the suction side. Okay, so be careful about how your rotation, that's what is happening. Many times looking to this blade, people they are getting confused with. There is nothing to confuse here. Like, we need to realize what we are doing. We are taking the benefit of our lifting force, we are taking the benefit of our force in order to compress the working fluid, in order to get the expansion work. So this is what I say as a compression work, and this is what I say as an expansion work. Okay. Now here in this case, if you look at, we have discussed in last session for say momentum. So we are having two forces. One, that's what is say axial momentum, and second, that's what is tangential momentum. So basically we have discussed my tangential momentum, that's what is helping us in order to have your torque to be supplied to your blades or your rotor. Okay, so basically your compression work, that's what we are getting because of this tangential force. Okay. Same way, if I am talking about say second force, that's what is say axial force. This axial force, that's what is useful to us in sense of generation of the thrust. Now let me tell you, those who are from aerospace background and when they are referring the book and literature and when they are learning, they are having understanding that thrust, that's what is being generated by the nozzle. That's what we are writing as say m dot into exit velocity minus flying velocity and my pressure drag. But that's what is confusing. You need to realize for gas turbine engine, all the components, that's what is generating the thrust. So we are having thrust generation by my rotors and my stators, okay, for compressor. Same way thrust will be generated by your combustion chamber, thrust will be generated by my turbine, thrust will be generated by say connecting duct, thrust will be generated by say your nozzle, and that's how we are getting overall thrust. Okay, so maybe if possible just go through the literature and read again. So here I want to say what is the benefit of using of our tangential force and axial force. Okay, so this is what is now giving us idea, like for compressor we are having our blade, that's what is low cambered blade, or say it is low cambered airfoil. So what I am naming here as camber, we will be discussing very soon what is that. Okay, now let's try to understand what exactly is happening on my blade or on my airfoil. So this is what is one of the good figure, that's what is available online. You can see here for this, say this is what is say my suction surface, on downside I am having my pressure surface. Now my flow, that's what will be incident here. So this point, that's what we say as a stagnation point. Okay. Now from our understanding, what we learn, suppose if I consider at infinite height, I will be having say streamline, that's what is a parallel streamline. And here if you look at when I am moving towards my leading edge, this region, that's what is called leading edge, and this region, that's what is called trailing edge, and distance between this leading edge and trailing edge, that's what is called chord. Okay, so what is happening near the leading edge, because my area, that's what is getting decreased, I will be having my acceleration of flow, that's what is happening on my suction surface of the blade. Similar situation, that's what is happening even on my pressure surface. But as I told, our major concern, that's what is happening on my suction surface. So what will happen initially up to some distance, I will be having laminar flow on my suction surface. And here if you look at, since this is what is a solid body, I will be having the growth of my boundary layer all the way from my leading edge towards the downside. Okay. Here somewhere if you look at, we are having say thickness of this airfoil, that's what is maximum. So this is what is a region where I will be having maximum velocity. So let me put the velocity on my suction surface. So here if you look at, say we are having our velocity, that's what is flowing, or say velocity with which my fluid is flowing on my suction surface, that's what is saying me it is the acceleration of flow. On later part what is happening, now you can see this particular passage, that's what is shaped like a diverging passage, okay, or you can say it's a diffusing passage, and that's what is happening. I will be having my deceleration of flow from say maximum thickness towards the trailing edge. So somewhere here I will be having lower velocity. Now when we are having acceleration, and later on, since we say I will be having this flow passage as a diverging passage, my flow structure, that's what is changing. So initially I will be having my flow to be laminar flow, later on it will go in a transition mode, and downside if you look at, my flow is a turbulent flow. So mainly when we are discussing what is happening on my blade surface, we used to say we will be having up to certain length laminar flow, after that we will be having short length for transition, and immediately that will be going for the turbulent region. When I say it is going under turbulent region, and when we are having this as adverse pressure gradient because of diffusing passage, so at some distance on my suction surface I will be having the flow separation, that's what will be happening. So somewhere here, that's what is called say stall point, or we can say this is what is say inflation point, from where I will be having my flow separation, that's what is happening. Now what is happening, because of that, my flow that's supposed to be follow my trailing gauge also, it will not be following my trailing gauge. So flow that will be coming out with different structure, that's what is defined as a wake structure. Okay. Now let's see what is happening on my pressure. So initially when I am having my acceleration of flow, that's what is happening in the initial length up to maximum thickness, where I will be having say decrease of pressure. And if you recall, when I was discussing about the construction of axial flow compressor, that time we were discussing my flow that will get sucked from this leading gauge, and that's how the flow continuation, that's what is happening in our axial flow compressor. Later on we can say, since my velocity it is decreasing, and this passage, that's what we say, we can assume that to be diffusing passage, I will be having the rise of pressure. Okay. Now this is what is very interesting and very important case. Okay. Now on downside, if you look at, suppose say I will be using my pitot-static tube, and if I will be measuring my velocity in the downside, you will see this is what is my nearly uniform flow on both the side, but within this region I will be having the deficiency of my velocity. Okay, and this is what is known as a generation of my wake. Okay, now when we are discussing about the airfoil, you will get shocked, you will say like, what is the use of all these phenomena? We will be discussing very soon what is the use of what flow, that's what is happening. And let me tell you well in advance, we are preferring to have our flow to be more turbulent on suction surface. Okay. Now let me move to the next slide. Say this is what is discussing about say my work limitation. What is my work limitation? We say in order to achieve high pressure ratio, or in order to achieve high work done, you are looking for my delta beta angle, that's what is one of the parameter. Suppose if you consider this is what is say my normal condition. So normal condition in the sense, I am having my area A1 at the entry, my area A2 at the exit, that's what is giving me diffusing passage. This is what is working absolutely fine. You can say this is what is unstall condition, where my flow is following both the walls. Now going aggressively, and you say please change the angle, blade angle. So this is what is say I am giving excessive turning to my airfoils or my blade. What will happen because of this excessive angle? I will be having my flow separation, that's what will be happening on my suction surface. So you can say this is what is putting limit to us. And that's the reason, as I told, compressor, that's what is working under adverse pressure gradient, and if you will go aggressive in sense of loading or in sense of achieving high work done, you may need to pay in sense of flow separation. When I say flow separation, the terminology we are using in compressor, it is called stalling of my compressor. And if it will be going for stall for some time, it will immediately go under surge condition, and there may be chances your engine will get fail. Okay, so that's the reason why I say this is what is a heart of the engine. Compressor always is a heart of engine. If it is not working fine, your engine is of no use. Okay, so that's the reason why whole lot of efforts people they are putting in sense of designing axial flow compressor in more systematic way, in more aggressive way with detailed understanding. You will say let's try to put this tilt this blade or stagger this blade in this way. By doing this, you can say we are able to increase the length of my stage. Okay, so this is also one of the way, but when I will be going with this is also giving me the separation of my flow. That's what is happening on my suction surface. So as I was saying, we are always correlating our fundamentals with the fundamentals of diffuser. So here if you look at, this is what is giving me what I am talking in sense of when I am changing my blade turning angle. So this is what we have discussed. If my length, that's what is shorter, okay, my diffusing length, that when it is getting shorter, I will be having a separation problem. When I will be going with say longer length, I may not be having the problem with the flow separation, but that's what will be giving you, or it's asking for the more space. Okay, so this is what is all fundamentals. That's what we need to learn and we need to understand. Okay, now let's move towards say now aerofoil we have introduced. Now these are the list of aerofoils what people they are using these days for compressors and fans. So here if you look at, this is what is say C4 aerofoil. That's what people used to say, it's a British aerofoil. This aerofoil say NACA 65. Say this is what is a family, that's what was proposed by say Americans. Okay, so these are NACA aerofoils, NACA 65. And here if you look at, we are having NACA 65 aerofoil. This is what is a second kind of aerofoil in which we are having say double circular arc. So here if you look at, I am having one circular arc here, I am having second circular arc here. That's why it is called double circular arc aerofoil. Now with the development of computational facility, computational techniques, people they are able to design systematic blades or say aerofoils. So this is one of its kind, that's what is called controlled diffusion aerofoil, where they are managing the flow systematic way both on suction surface and pressure surface, and that's what is giving the benefit in sense of increasing the pressure ratio or pressure rise for particular design. Okay, so this all aerofoils what we are saying, they are say subsonic aerofoils. Okay, so these aerofoils when we are designing say low speed compressors, we are using these subsonic aerofoils. Let me tell you, when we are talking about say HP compressor, that is high pressure compressor, in that high pressure compressor I will be showing you the blades in next session where we are having the aerofoils of this kind. Though we say this is what is rotating at the high speed, but still we are having those aerofoils to be subsonic aerofoils. Now if you look at here on say our right hand side, we are having double circular arc, that's what I told. Now in last session we were discussing the limitation of high rotational speed and higher axial velocity, and we say my flow that's what is going transonic, and that's what is increasing the losses because of my shock formation. Okay, and that's the reason it is reducing the efficiency. Now you can understand when you are going for more aggressive way of designing, in order to meet your future requirements, you need to do your R&D, and that's how people they have come up with different kinds of aerofoils. So if you look at all these aerofoils, they aerofoils are transonic aerofoils. Okay, so here if you look at all these aerofoils, they are having their leading edge and trailing edge, they are sharp. The purpose here, it is to attach the flow or it is to attach the shock. Okay, when we are having our sharp leading edge, I will be having my shock that will be attached with the surface of my blade. Okay, same way for trailing edge also. And here if you look at for say subsonic aerofoils, where we may be having say circular leading edge, it may be having say elliptical leading edge. Okay, their purpose that's what is different, where you are looking for different kind of application. If I will be using say subsonic aerofoil for say supersonic or transonic flow, you will be having formation of bow shock. That's what is undesirable, that's what is not required, because my flow physics downside of my bow shock, that's what is not favoring the reason for what we are using these aerofoils. Okay, so here if you look at, this is what is a multiple circular arc aerofoil. You can say this is what is my one circular arc on suction side, this is my second circular arc, I am having say third circular arc, and this is what is my fourth circular arc. So this kind of aerofoils also people they have designed. Okay, not only design, say people they are doing say initial design, then after they are doing their testing in cascade tunnels, and then after with the database what is available to them, they will be using that for application for design of say rotor as well as stators. Okay, we will be discussing all this in detail as and when this session, that's what will be coming. We have one special session that will be talking only in sense of transonic compressors. Okay, here if you look at, this is what is a systematic way of using multiple circular arm. This is what is, say, S-shaped kind of airfoil. So earlier people, they were talking, say, for high bypass ratio engine, for low bypass ratio engine, we know my flow will be going transonic near the tip region, where they used to use this transonic airfoils. Now with the maturity of technology, with use of your computational tool, with more detailed understanding of flow physics and good experimental results, people, they are able to design the, say, blades of the fan. They may be, having, say, flow, that's what is transonic, and in that transonic region they are using this kind of airfoils. The pressure ratio as on today in multinational companies, engine making companies, they are claiming that's what has reached to around 1.8 to 2. So you can understand, day by day people, they are going very aggressive in sense of doing the design of these compressors. Okay, so this is what is called, say, your transonic airfoil. Okay, so we are having subsonic airfoils, we are having transonic airfoils. So initially when you will be doing your design, you will be taking one of the standard data, that's what is available to you, okay, in open literature. Okay, then after, as per your requirement, you need to modify the shape of these airfoils. Okay, that's what is called custom tailored airfoil. That's what will be giving us the idea in sense of what we are looking for, that's what we are achieving. Okay, now let me put the point here. Say, in order to use, in order to design, in order to meet the competitive market, as I told, the multinationals, they are working a lot on design and development of this kind of airfoils. Okay, so if companies, they are registering their patents, most of the patents, if you look at every year, those are going to this airfoil development. Okay, so they are making new kind of airfoils, and that's what they are using for design of their compressors, design of their fans. And if you recall, I was showing you two rotor blades for fan, in which I was discussing, say, near the hub region or say near the end region. If you look at, for the hub region, we are having our flow to be subsonic, where we are using this kind of airfoils. And when I am talking about, say, my fan, that's what is having, say, larger diameter, or my blade height is larger, near the tip region, above 80%, 85%, if you go, your flow will go transonic, and in that region we are using this kind of airfoils. So you can understand, it is not always that your airfoil is uniform at hub, at midsection and at the tip region. It may be possible that you will be having different kinds of airfoils at different locations. That's what is putting more challenging part in sense of design, in sense of understanding, in sense of fabrication. So you will be making rotor, that's what is having different kinds of airfoils. When you will be going for, say, fabrication part, it may be possible that it will be more challenging to fabricate those kind of blades. Then again you need to reiterate your design. Okay, so mostly for high bypass ratio fan, you are having your subsonic airfoils near the hub region. You will be having your transonic airfoil near the tip region or shroud region. And for, say, high speed LP compressors, throughout the span they may be going transonic. Okay, and when we are talking about high pressure spool or high pressure compressor, most of the stages they are going subsonic. Okay, so here we are stopping with, we have discussed today about what all are the benefits of our lift force, that's what is to use the airfoil section. Then we have discussed what is happening on our suction surface of the airfoil and how this suction surface, that's what will be helping us in sense of achieving what we are looking for. Then we have discussed about different kinds of airfoils, what we are using for our axial flow compressor and axial flow fans. So here we are stopping with. Thank you very much for your attention.